Now, we have Agnes Maida here, aka Mel. She's going to talk to us a little bit about parallel programming. And because we know that serial programming is totally last decade, rock 'em parallel graphics cards.
Thank you for having me. Thanks for having me, and I would especially like to welcome our stream watchers, especially the ones in China and Beijing. Hello! But they are probably watching it tomorrow. Hey, come on, I'm on the off. It's just on the wrong position, probably. So should I put it on my glasses or what? Sure. Pooh! Better? So we are going to start again, and now it's apparently I hear more of myself, which is perfect. Again, I would like to greet the Chinese peace mission in Beijing. I'm very happy to see you here. I'm going to give you a short overview about what's happened until now in parallelism and what is going to happen in the next few years. And I hope you will get a firm reality check if it's worth the work, actually, or if you actually have the problem for investing some time and energy into changing your code to fit to the needs for parallel programming. And because my battery ran flat on my presenter, I do a little dancing around. First we do a little bit of motivation, then I will shortly explain some basic words about parallelism so that we know we are on the same page. Then I will talk about the old standards, old in means of single multi-core parallel programming, and then I move over to accelerator cards. And hopefully you will have a new picture of the whole story. In the end, there will be 10 minutes Q&A, hopefully, and my herald will make sure that I will get to these 10 minutes. So first, motivation. Why should we bother doing parallel work besides playing computer games? Well, I'm in research, so what we tend to do is probably analyze the so-called big data. I'm not a huge fan of the word big data because it's basically a buzzword for pattern recognition in large data sets. And some people think it's the new crystal ball. Yeah, okay, you could do big data with huge parallelism. But you could also do something, in my opinion, more meaningful. You could do physics. In this example, this is astrophysics, which always creates wonderful pictures. But they do some Higgs boson analyzing at the CERN or so, and they have huge machines working on the large amount of data their accelerator creates. But I'm not talking about, you can also do some weather calculations with it, but I'm not talking about them because here at the University Hamburg, they don't like accelerator cards because they are very energy intensive. So they are against them. But what I do in my work is actually we are trying to simulate protein flexibility. I'm a bioinformatician. I'm a PhD student at University Hamburg. And we try to figure out how molecules move. This is a molecule which is very relevant for your heart. This is very important for depolarin, your membrane, so that your heart actually beats. If this thing is broken by a medicine you take, you will die by a heart attack. So to understand this protein, this channel, it's very important to know its structure, difficult to determine, or to simulate its movement. Actually, you can here see a picture from above. The red colors mean that it's in the closed state, nothing can pass through. The green state means it's in the open state. Now the ions can move through and then repolarize and depolarize the membrane. This is a very essential state in your heart. So you really don't want to create medicine that works against this one. And if you could make the prediction methods better so that we can sort medicine out that works against these stuffs, we could make medicine a little bit cheaper, medicine development. Which means also that my university sends me to summer school so that I would get a better overview about the future trends and the current trends, which means I now have to show you my sponsor logos, you know. So I'm funded by the Federal Ministry and a third party, which means Bio Crop Science, and I'm a PhD student. Hamburg University, which also means I'm a member of the CCC-HH. So, let's get to the real topic. Let's talk about parallelism. So that everybody can follow. I created a wonderful, colorful picture, and we will go through the details. We will reconstruct this whole picture in the talk, and then we will hopefully you can see how it fits all together. But we will start on a very simple level. We will just start with the headline. Because we need to discuss what database and task-based parallelism in my definition is. This may not be the best fitting words, but this may be words that you can associate with something. And in my mind, these tend to associate with food, because I'm a very food-oriented person. When we talk about data parallelism, it could be associated with frying a lot of omelets. Your data is the respective egg you need to fry the omelet, and you have to do a lot of omelets to feed a lot of people. Task parallelism means that you would like to cook a 5-course menu for one person. You have a lot of tasks you need to do, but you have only to deliver them in a certain way, but you have to cook them in a different arrangement. You can definitely mix them up, obviously, in increasing the number of people for whom you are cooking. So data-based and task-based parallelism are not a contradiction, they are a combination. Good. But obviously, you tend to have problems when you start to cook for 8,000 people. A 5-course menu from one menu piece is an omelette. First of all, your kitchen could be too small. 8,000 people is not so fun. Also, you may not have chef cooks all the time. You may have apprentices. You also have probably not enough pans, and you don't have enough space to move from and to the fridges. You also have just probably one recipe book, and that means it's crowded when you want to read from it. You also need to deliver your stuff to the kitchen, to a specific spot. You probably have some problems transporting the eggs. And obviously, in the end, you somehow need to serve the course in the correct order, and it should be hot. But you can translate these problems into more techie language, which means you can say that your kitchen has a global capacity limit. Your apprentices are actually related to your complexity of the processor, which in our case means a single or double precision computation. You could have probably not enough frying pans, which means your card is just too small to cook everything at the same time. You can also have some bandwidth limitations. You have read-write access limitations you need to think about. And then you end up with probably coalescing memory access problems. Probably your memory works better when you access it at the same time with a large request instead of accessing all the time with small requests. So you should probably assemble the request for eggs and transport one big egg package, And in the end, cooking, you need to synchronize and keep the meal hot. So this problem were all the time here. So they developed some standards, some old standards, which were used by single and multi-core clusters in research, where I'm part of, to use their computational resources the best way. The old standards, which are not so old, but we are living in a fast-developing age, are OpenMP and OpenMPI. And you can see with the different colors and the different shading, they are on two sides, so data-based and task-based. And the one, OpenMP, the red one is on the implicit, which I would say it's on the high-level way. You will see what I mean when you see the first line of code. First of all, we would like to cook our menu. General 5 courses, how do we do that? For this, we use OpenMPI, because we need to dispatch a lot of tasks, and OpenMPI lets us do this. Just imagine that you have a cluster of many single-core or multi-core machines, like 2008 probably, or 2005, and you would like to cook a course of a 5-course menu. First of all, you install it, which is what I'm not talking about. But then you have this line, the last one, that says how to run the code. And this starts with MPI run. And then you have an abbreviation for a number of processes to launch. You could set it on 1, or you probably have 5 computers, 5 cores to use over your distributed net, so you could set it on 5 or 8, what you can think of. And then you have a -host file, which will read a text file in which you write down the names or addresses or whatever of the computers you would like to use for your task. And then OpenMPI will execute the program on the specified computers with the specified amount of processes. And it will loop over the names in this host file. So you probably have more processes running on one core than on the others, because it has to probably loop over. This is different to the POSIX thread and Booth thread library, because OpenMPI gives you an interface for message passing. So when you execute this, when you start it, it actually starts to create a message queuing system so that the respective processes can send data and exchange data with each other. Actually, when you think about it, the code to do this is actually quite short, because you just init, here you are. You, no. I have poor vision, so I can't read that. To do this in a different way. You first init the MPI, so it will start the queuing, the message queuing system, and start with a lot of overhead. And then you realize in line 10 and 11 how big your world is and where your position in this world is. And then you can start communicating, an example, informing the user where this thread is actually was launched, and then you can probably cook your menu. This is how you do a task-based model, and I don't think there is yet a new implementation, a real one in C, C++ for this. So this is still standard and high-tech and very often used. And you finish, obviously, with MPA finalize, and after that, your MPI program has switched off its message communication, etc., and will just run on your single core again. So this is short and this is sweet. So let's look now how we fry an omelette. Let's go over to the old standard how to do data parallelism. Obviously, when you fry an omelette, you need eggs and a pan, and then you need to apply heat to get an omelette, which is basically matrix multiplication. I mean, it's obvious, right? You apply some heat. So, if you're not so familiar with matrix multiplication because you don't move a lot of indices, this is your helper slide, and I also uploaded these slides into the FARP system already. So be sure to download them and look back if you're lost. This is really, could be a bit tricky for some people. So matrix multiplication actually means that you produce the product, the sum of products of parts of the matrix, and I colored the respective necessary rows and columns to compute the element in C, the resulting element in C. And you do that in picking the first element in A and multiplying with the first element in B in the colored area. So you move in both matrices over K, while I and J are fixed. This is important. So you realize that actually, to calculate this specific spot, you are not connected to the calculations for other positions. So you actually, it doesn't matter when you calculate the respective C part, you just have to do it some time, and you need a specific amount of data, okay, but it doesn't matter. You can do this in parallel. And actually, in image processing or in scientific computing, they do that a lot in parallel. And you can obviously code it. And just for reference, I'm showing you the tested C code, which is just full, like you need to, yeah, exactly. So you need to define your matrix, and there's In line 3, there is a known prerequisite for multiplying matrices, so please know that, and then you just go over the loops, fix A and J, and then go over K and produce your sum product. So we will now transform, most of the time, this code into the respective parallel versions. First of all, to run OpenMP on a multi-core processor, you should probably test if it's working. So you write a hello world here, and you can ask the system if it actually did work. As you probably can already see, I included a header there, OMP, for OpenMP, and then there's not so much code, there's just this weird pragma in there. And this is how you code OpenMP. OpenMP is translated by the compiler to actual code, so the compiler decides how to parallelize it. So you inform him, hey, now comes some parallel stuff, please execute it parallel on the amount of processes you have in your system, and the compiler will decide how many processes there are and how to distribute it. But it's very short and cute, and you can see the code, instead of focusing on all the overhead stuff you could do, and we will see in CUDA how it could look like. If you now do some real matrix multiplication with OpenMP, first, you have to probably fill your matrix. This is why this is the less important slide. You have to I got these words. You have to fill your matrix with data, apparently. The important slide comes now, because now you have to compute. As you can see, it's basically the same code as in the normal matrix multiplication. I just wrote an OMP parallel above it. Yeah. Now, who's seeing the flaw? Okay. When you free it, then, that's the end of it. You can print it out and free it. But actually, what it does, it will give you a printout. And it will tell you, hey, come on, I have 4 threads. This is thread 2, and I'm computing this and that value. And then the next thread will say, oh, I'm computing that value too. I do that too. This is not what you want. So just writing a parallel over it will execute the code on parallel, and apparently this is a quad core. And so we should invest some more letters into our pragmas, and we did that. We defined some helper variables here, the example, the chunk size and the IEJK, and then we extended our pragma. Now we tell it that, first of all, the next following block code is in parallel, and some of the information, like the matrices, are shared. Everybody in this whole compute unit is going to use them, but J and K are private. And then we inform it that here, there's a second pragma in line 11, that there is a for loop now coming. And this for loop is important because the I that defines this that runs through this for loop is defined as shared. So this means that the 4 threads that will run and compute these values will not calculate, will not have the same I. So they will be different, and this is what we want. But they will iterate over the J and the K, and they will not change anything here. And you can also define how OpenMP schedules all these things. So this is way better. This is what we want. And one word for scheduling. It could be dynamic, and you can also, dynamic means it checks if the respective thread is done, and then it will load another pair of data on it for the computation. And it will load the amount of chunk into it. So it will compute, in our situation, 4 values, 4 I's via this loop, and then request new data. You can change this. You have a little bit of overhead when you launch new processes here, so you should choose the value wisely, and especially check the time. You may be a bit irritated how different it could be changing the chunk size. This also is relevant for CUDA. Obviously, you have to install it first, and you have to use, in this case, GCC to link it, and yeah. These were the old standards, and now we are going to accelerator cards. We are back to the picture. And now we are going over to the explicit models where you really have to look into your data, move the data, allocate stuff, and so on. So this really C way of doing it. And I'm perfectly on time, which is great. No, that was one too far. Yes, we have to make sure that we don't miss the words. We are always on accelerator cards thinking about a host and a device. The host is, in most cases, the CPU sending off work to the device, the accelerator card. In most cases, which you are probably used, these are graphic cards. And then, when you send something to the device, you send over a kernel, which is a function which is launched on the device. So if I'm now switching to kernel, this is just a name for a function. Yes, and when you're running Linux, you need to install the proprietary graphic card drivers, which actually worked out very fine on my system. But not on my work system. So first of all, we can do this now in CUDA. CUDA is the programming language developed by NVIDIA. They do invest a lot of marketing money in sharing it with all the world. They have a lot of great documentation about it. Yeah, but you should choose wisely, you know. But you will see it's actually quite nice. This one, what you can see here is first of all the kernel. It's going to the device, which means it has this global keyword in front of its definition, with this double lines there. And then in line 8 and 9, it somehow tries to calculate a row and a column. And it does this in requesting something like a block ID and a block dimension and a thread ID. Well, obviously, we are talking later about this, you have graphic cards with a lot of parallel processing units. There are a lot of them, so you need to number them somehow. And there are different ways of doing that. You can do this in 1 dimension, or in 2, or in 3 dimensions. And this is how you compute the global index of your respective kernel launch. And then you may need to consider what you're going to do this, depending on which position you are in this process, which happens here because it uses this computed number row and col to define which part of the matrix C it is going to compute. So I now have to warn you, my work PC didn't like my linker, so I wasn't able to test this, but you can find a better example on CUDA. So I may have switched the indices. I can't guarantee. This is really tricky. This is the worst part of CUDA programming. Okay, but we also have to initialize on our host in our main function, our matrix, and then we have to, in line 9 to 11, we have to allocate memory on the device, and then we have to move the knowledge, the matrices A and B, to the device per hand. This is CUDA style, you know, we are explicit here. And then you have to define in line 17 and 18, your way how to figure out what each kernel launch has to do. So you need to say in how many dimensions you define the indices you're working with, and this is done with this dim grid, dim block thing. Currently, as you can see, my dim grid is just 1, 1, 1, but my dim block is exactly the size of my output C, just in 2 dimensions. Not so nice. We'll talk about that a little bit. So this code is not safe for work if your C is too big. Okay, but when you have decided how you would like to number the threads that are running on your graphic card, in example, you have to launch the kernel and inform the kernel how it's going to be addressed. You know, you tell it how is the numbering of the respective launches going to be. And you just put in the input, the matrices to be multiplied, and then the kernel starts to compute the respective index and so on. I think I have a summary slide of that too. Okay, after you've done your computation, you need to synchronize again. You need to fetch the memory from the device to the host, and then you do something with it, you free your stuff. Yeah. So if we summarize, the important parts are here in CUDA. First of all, you have your kernel above there with your indices computation, very relevant and very problematic. And then you have in your main function the question how you define your dimensions, how many threads you need to launch, and how you adjust them. So you have to fit line 1920 to line 3 and 4. This must fit, and this is a case for pen and paper. And then you launch your thread and your kernel, and then you synchronize the threads to make sure that you're done with the computation. This is basically CUDA style. But there is, I see, this is the installation sprint. I cannot guarantee you for the linker command it should work like this, but I couldn't reach my sysadmin at work. At work I have a CUDA card, and at home I have an OpenCL card, and my work configuration is a bit off, I think. So now comes the other version of programming accelerator cards, which is called OpenCL. For this, I used the nice code from the source I linked here, but he can't come today. Very sad. I asked him about it. And it's actually just a vector addition, but you will not really miss it. OpenCL is a language that is developed by NVIDIA, AMD, ARM, etc., so that it will fit to a lot of devices, basically devices that have a core. So it is very flexible about the device that it has to run on, which means you have to tell everything to the programming language, to your kernel, so that it knows how to execute. First of all, obviously, you have to allocate your memory and put some stuff in it. Then you have to, interestingly, you have to read the file where your kernel is programmed into your system. And then on line 14, you have to figure out on which device you're actually running, and yeah, the ID stuff. And then you have this device ID thing, which is actually kind of interesting in line 20. I will repeat this line later on. I will talk 2 more sentences about this. And then you have to create an OpenCL context, put everything together. And then you have to start a command queue. You have to then write over the memory and allocate memory for it. Then you have to create the program. Then you have to, I have to read it up, you have to build the program, and then you have to create the OpenCL kernel. You know? I mean, don't mix it up. Then you have to set the arguments of the kernel, because it doesn't know it apparently. And then you have to inform the system how big of chunks, probably, you have to calculate it. So you have to inform it how big the overall size of your vector in this case is, or of your matrix. And you have to tell it in how many pieces one thread should execute when it's started. And then you launch the kernel. Great. But now we have launched the kernel, we have to get the memory back. So you enqueue your read buffer, and then you need to delete everything and release everything, which is also a lot of code. So, yep, as you can see, OpenCL needs a lot of code, but because you can configure so much, you can use it on a lot more platform than just NVIDIA graphic cards. The very interesting thing about it is actually that you, in line 7, can switch the CL device type GPU to CPU, and then you can execute your program without any problems on your multi-core system. And then you can use your normal debugger for debugging it, which is quite nice. And you just have to change this line. So, exactly. So, you obviously already has to install the Kronos OpenCL headers. Kronos is the group in which NVIDIA, ARM, and AMD and others are developing this OpenCL language. And you have to compile it. It's already in the GCC. Yeah. So the next slide is going to be, yep, this one. So in summary, we always have the same code, but in reality, it may look a little bit different. So you have to define your accelerator device, either explicit or implicitly, And then you have to move the memory, launch the kernel, and tell how many launches it should have and how many data it should process in one launch. And then you have to clean up with more or less code. You can wrap a lot of OpenCL in special functions, so it stays flexible and looks a little bit more cleaner. But when it's about cleanness, we could also look at OpenACC. And this is the new standard situated next to OpenMP. So if you can remember, OpenMP was about this pragma stuff. OpenACC is a similar thing in blue, just for accelerators. They are aiming to fuse it with OpenMP, but it's not so really working right now. But because it's short, and you can then see your actual code, I will show it to you as well. This was the matrix multiplication in OpenMP. And you can see there is this parallel shared and this for loop pragma thing. And then we take this one and we convert it to OpenACC. We just switch the OMP to ACC. And we are pretty much well off here. Again, in this code piece, like in OpenMP, OpenACC is actually compiled to OpenCL code, or depending on the compiler to CUDA code, when you compile it. So this thing will be translated into an OpenCL code, hopefully fitting to your accelerator device you have defined on your compiler line, which means you can compile it for a lot of devices instead of for the one that you had in mind. Which is, in most cases, better because you can be more flexible in your development. So after OpenCL, I think this is kind of relaxing. And it's quite interesting. You can get OpenACC currently only in compilers for which you have to buy some licenses. But since November, there is an email exchange on the GCC mailing list that apparently OpenACC is moving into GCC in the next 12 to 15 months. The first patch is already submitted, so we can hope that it is available for people who don't have a lot of money for buying all these compiler licenses that we apparently need. Okay, so this is OpenACC. But the world does not only consist of stupid matrix multiplication code like the one I showed you. It actually is a bit more difficult because your matrix could be too big for the device. So you actually don't load the whole matrix into it, you just load tiles into it. And then you have to walk through your matrix like shown, so you move from one piece to another piece and be a bit more brainy about it. Exactly. So you have to be a bit more specific about your threads and be careful and so on. This is also a part where you need pen and paper when you start to program it, because you can mess up some indices. There's another problem with it. And this is, in CUDA terms, it's called warp divergence. Because actually, if you at least look at the graphic cards by AMD and NVIDIA, you can see that that they are hardware, how do you say that? They are threads combined by hardware. So you define the amount of threads that work together, that are launched simultaneously by your head in your code, in your main program when you define your dimensions of the grid and the block. But actually, NVIDIA as well as AMD also have a hardware encoding of these sizes of these. And in NVIDIA, it's 32. This means that they will always be executed in blocks of 32 threads, and you should choose a block size or a grid dimension size of 32 or more, multiplies of 32. This also means that probably your tile doesn't fit when you do a tile matrix multiplication to your matrix. So you have an overlap, and now you need to think about what you do when you have an overlap. Because when you have an if-else branch in a warp, this means that you first every thread in this warp will execute first the first branch, the if branch, and then the else branch. So the ones that have something to do in the if branch will work, the others will sleep. And when the others that have something to do in the else branch, they will work, and the others, again, will sleep. We will lose some efficiency. So you should think about of just probably, in this case, entering zeros in the pure blue parts, or somehow figuring it out. Warp divergence, which means if-else branches are not nice. It's better to recompute than do if-else branches. This also holds true for not just warps, but for your whole block. They just can work through one instruction with a lot of data, so they have to work through each line, and some of them will be idle. So if you choose the block size not very wisely, you may have a lot of sleeping threads the whole time, and your device seems to be busy. You should look out for that. Then there's another thing which I didn't cover in my code. Actually, in example, NVIDIA GPUs have a global, constant, and texture memory, which is accessible for everybody. And then they have shared memory, which is just accessible for the ones which are organized in one big block. They are grouped together, the warps, the blocks, so they can access the same shared memory. And obviously, it's way faster to access the shared memory than access every time the global memory. So you first load the piece of the matrix into your global memory, and then you load the specific tile of your matrix into your shared memory. And this is the speed up you should aim for. But this can be, depending on what you actually do instead of matrix multiplication, can be tricky. And how much speed up you can get changes with every generation of, in example, the NVIDIA cards. So probably the speed up you got with the last generation card is not going to work with the next one because they have better memory access. Which is why I am actually rooting for OpenACC. So just an information for the ones that are looking into these programs. They do not have a very nice naming. They have decided that in CUDA, a thread is a thread, and you can combine threads into a block. Actually, blocks consist of warps based on hardware situation, but threads are in a group. These are blocks, and then you can order blocks into a grid. Fine. OpenCL has decided that threads are actually work items, and work items can be grouped in work groups. They don't know a grid. And OpenACC thought, we need to somehow accept every definition. So we do a vector, which is a thread, fine. And then we somehow say there are workers, and then there is a gang. And you should, at the moment, never use all three ways of defining how your kernel should launch, just two, please. So it could get a bit tricky if you switch between the various documentations. Just imagine you have to count through the amount of threads you're launching, and you have to address them, find them again, and so you have to use some pen and paper and find the fitting words in the respective documentation. So, but we should cover hardware, and how many minutes do I have left? Wonderful. This is great. Hardware. You've heard a lot about graphic cards, and there's also the talk about this Xeon Phi thing. And then there's something a friend of mine, actually my boyfriend, recommended to me, which is called Parallella. And I will not cover FPGAs, but everybody who looks into parallel computation of stuff, of algorithms that they can encode into hardware, FPGAs are so fast, you should think about it, and they are cheap. But if you need a CPU, a flexible one, you need to look into the three other ones. First of all, you probably all know how these graphic cards probably look like. This is a very interesting picture of a Tesla card. Tesla cards could cost around 2,000 euros, so if you don't have the money, I'm sorry. But you could probably use your graphic card, which you already have in your computer, AMD cards look somehow similar. They all have these green vector units. They all use, which is blue, exactly, right, the caches. Then you have a dispatcher unit, and then they are somehow communicating with the global memory and fetching some memory here and there. I'm not talking about the possibilities of reaching that and that, how many gigaflops and how many computations per second, because reality shows that you actually need to have a problem to get to these numbers. If your problem doesn't fit, you just don't need to care about the gigaflops that your card could maximally reach, because you cannot reach it. Because in example, my protein is not so big. Then we have the Xeon Phi. This is a very, very special, different architecture. You don't need CUDA or OpenCL to program it. You just need simple C or C++ code. Because it's actually consisting of 61 or more, depending what Intel sells, normal cores connected with a cache. And then they are all, as you can see in the above picture, they are all connected over a ring. So, and they access this ring via a bus, which means if you do not have enough threads to use every core in this loop, your memory bandwidth will drop. So think about it. It's really nice that you can use your normal C code, your normal OpenMP, OpenMPI code on this, so you don't have to rewrite a lot. But you need to think about if you really can reach the memory bandwidth that you are aiming for. You need enough threads. If you then look into the processor, the lower picture, you will probably realize that this is a quite old core design. I think it's a Pentium design. And you can see it can execute 4 threads on the top there in parallel. It has 2 pipelines to actually pipeline the whole stuff, but there is just one pipeline with a connection to your vector unit. And your vector unit is the one that executes code in parallel. So again, you need to put enough work into this vector unit to make up for it. So it's not perfect, but it's great because this card runs Linux. You can open a shell with it. You can work with it like a normal cluster. So your migration efforts are way smaller than you might think. And then there's this one. Oh yeah, by the way, Xeon Phi, it's probably €2,000, but I haven't met anybody who actually owns it. There's this sweet card, Parallella. As you can see, it's $99, which is nice. It has a combination of an accelerator board on it. The accelerator card is Epiphany here, there. And it has 16 to 64 microprocessors on it. It can understand C, C++, and OpenCL, so not so bad. It also has an FPGA. And I read if you don't use the HDMI output of this small little card, because actually this is a huge computer, a full computer, then you have around 70% of this FPGA for your own use, which is interesting for figuring out. And it also has a processor, a dual-core processor. And it's just $99. So I would say this is something for our maker community. You can do something with it. The only thing is, at the moment, I think they have already sold some pieces, but the pre-ordering for the new model is closed. So probably they will open up in January, and then you can shop and try out your own stuff and have a little small cluster at home. Would be cool. So now the picture is again complete. I just added, just in the middle, the C++ AMP, because I was talking a lot about NVIDIA and AMD, but you should never leave out Microsoft, because there are people who need to develop on Windows, even for parallel applications, and Microsoft has developed an extension for C++. They are shipping it with Visual Studio 2012. Apparently, it is based somewhere situated in the middle, because it means that you can go towards explicit programming. You can really force it which threads should execute in which combination, in which size on your device, but you don't have to. So if you are going towards Windows, you can use C++ AMP. Look into it. I don't have a code snippet there, but it's online in the documentation. Exactly, I would say. And then we are coming already to the end, I think. Yes, the end, which is great. Because I did not mention, in example, POSIX threads. I did mention them in a small sentence. I did not mention boost threads. You know, these are all more on your, these are thread libraries for your system. They are not aimed for running on a huge cluster of a lot of nodes. So they don't bring this whole message passing interface for easy communication with them. So I don't need to cover them. There's also something like called Silk. I think it's by Intel, and there's also Intel Thread Building Blocks. I've just seen it, so probably if you're searching for different alternatives, you should look into that. And I didn't talk about task scheduling programs, even though I love them. Because, and I apparently have 2 minutes left so I can talk about them, which is great. Task scheduling programs are the ones that you would like to have for deploying your programs on workstations of your users. If you do not know the workstation of your user, you can write a program based on StarPU, which is developed by the University of Bordeaux. And StarPU will first benchmark the PC and the device, the graphic card probably that's on it, and then decide how many data it will send off to the device and how many data it will be computed on the CPU. So people, your customers probably, with a graphic card with a high-end graphic card, could load off a lot of computation on the graphic card. People with a very weak graphic card will have the most computation on their CPU, which is nice and flexible. All you have to do is actually provide StarPU, or the program that you're writing, with multiple implementations, which will work then for the graphic cards and for the CPU. So probably one OpenMP/OpenMPI version for your CPU, and one CUDA OpenMPI version for your GPU, an example. This is actually very interesting, because as PhD students for a company, we should deploy software for a different set of customers, and if our software can actually somehow meet the need or the abilities of the respective customer's PC, I think this is quite interesting. With this, I'm done, and I would say it's time for questions now. Thank you for listening.
That was awesome. So for questions, yeah, just queue up at the mics if you like, and we could take some questions. All right, we have a question over there.
I wanted to know whether MOSICs and OpenMOSICs still exist, and do they know how to talk to graphics cards today, if they do?
You're probably talking about this, these versions that were before they tried to make this programming easier, and I don't know about it, because this would be too difficult for us to use. So we moved into this field when CUDA came, because, I think they're still alive, or somehow something like this are still alive, but I think they are losing now market share, especially with OpenCL.
Thank you.
All right, we have another question at this mic.
Okay, so it looks to me that, very roughly speaking, of course, OpenCL and CUDA, for example, compare like Java and C a bit, because both Java and OpenCL are more bloated in code, and what you get out of it when you compile it is more general code. But then we all know that Java may be slower than C, so I wonder, can you say something about how the performance compares, maybe in terms of some benchmarks, maybe also in comparison with the vector processing instructions like SSE that we have on modern CPU architectures?
Actually, I heard about a benchmark. Somebody ran a very parallel application, a full parallel application, a Monte Carlo simulation on a Xeon Phi, a CUDA card, and on the Sandy Bridge. This is a 16-core Intel processor, as far as I know, and I think we actually have one in our cluster. And a full parallel version, there the GPU would perform best, but if there would just be one iteration, one not parallel, you know, what? One serial iteration in this piece of code, the Sandy Bridge would perform best. And the GPU would be, even though most of the code would be perfectly parallel, would not perform good enough. So instead of investing so much time into optimizing for this CUDA card, or for, I think they had a Tesla, they said, nah, probably I should skip it and run buy me a Sandy bridge, which could be easier. There's also something, if you optimize your code for OpenCL, it will not run as good as for CUDA, and on the other way around.
So it depends on the problem, basically.
This is one thing, and it depends on you how much time you invest on optimizing for a specific card.
Thank you.
Okay, so we could take another question from there.
Hi. Did you also look into other programming languages that make parallel programming possible or even easier than with C, C++, CUDA, OpenCL and stuff, like, for example, Haskell with the libraries that they provide?
Because I'm bound through my project to C, I don't. There is another language, I don't know anything about Haskell, I just seen some of the lambdas, but Google develops Go, which is somehow a replacement for C++, which also I think aims to make parallel programming more easier. And also all the standards are also developed for Fortran, and I would really be happy if this light would just stay stable, really. So this also works for Fortran, which is what most physicists and mathematicians use. But no, not farther than that.
All right, one from there now again.
Hi, I have a question regarding OpenACC. Obviously, there's a lot of magic implemented regarding data flow analysis, and I wanted to know whether there's also some magic for in case your input or output doesn't fit into memory, like this tiling case regarding matrix multiplication you talked about, or is it, or do you have to handle it manually?
I think they do tiling, and it depends on the compiler. The good thing about it is that OpenACC is for the PGI compiler, which I saw. For NVIDIA cards, it's compiled into CUDA, so you can actually look into it. And for AMD cards, it's compiled into OpenCL, so you can actually read it before you launch it. I think they do an example tiling, because else you can't compute this matrix. OpenACC doesn't give you enough pragma possibilities to tell it to tile the matrix. So it needs to do this on its own. And the more trained the compiler gets, the better they will do it. So it has to grow with the community, I would say.
All right, cool. I think we have one question from there, and we have time for one from here, I guess.
Okay. I'm as advanced C, C++ programmer. I see in your examples a little confusing because you mixing integer and pointer. In this, my question target about is that it's fine on a 32-bit architecture, but the problem is if you're switching to 64, then you get a problem because the pointer will double, and the pointer size is now 8. And integer in all standards I know in C, in C++, defined as 4-byte types. So the question is in CUDA or OpenCL the integer are they defined, or is all defined that should be only 32-bit?
I actually cannot answer your question. I just switched to integer so that my written output on my console would be more readable. So it's like getting rid of the digits.
Because you said size of int, and you say then void star, and this is a problem, as my perspective.
Okay.
As a real world programmer.
Yeah, actually, yeah, I do program with floats, so it's just for this use case. I'm sorry. Okay. So it didn't broke my computer until now in my little examples. So I'm sorry. So please don't switch to make to big integer stuff, and be careful.
All right, I think we have one more from here.
I haven't worked with graphic cards, but I worked with parallel execution, and there it's most of the time I spend defining what are values, what are mutable values, and what needs to be shared and stuff. And in the code you showed, I've hardly seen any definitions of what needs to be shared among which and stuff. Can you say something about how that works on a graphic card? Or?
Yeah, I actually left it out so that it wouldn't be too complicated. What you do is you just use a specific keyword, in case of CUDA, in front of your, in your kernel when you need to load, in example, the small tile into your shared memory. So you use a specific keyword called shared, I would say, I think. And as in CUDA, you have to do this the same way you have to do this by hand. And in OpenACC, you could, it should figure it out by itself, but OpenACC also allows you a little bit, like OpenMP, to define for the system what is shared and what is private. So.
All right, that has to be our last question. And so please, on your way out, first of all, round of applause.